Thank you so much, and thank you so much, Dr. Tanvir and Siam, for having me. I'd like to share my slide. Are you able to see my slide right now?
Yes, Dr. Podal, slides are on the screen.
Okay, so a little bit of background about myself. I am originally from Nepal, so I'm very close to Pakistan, and I actually did my bachelor's in veterinary sciences and animal husbandry from Punjab, state of India. And then I worked in Nepal for a couple of years, and I wanted to do a postgraduate degree. And US was a great opportunity because there's a lot of opportunities here to come as a graduate assistant, and that takes care of your housing, your college expenses, and even gets you through your grad school. So I got my Master's of Science in poultry, and during my master's, I worked with lighting systems and how they can affect poultry. And my PhD was more focused toward nutrition, and I got this opportunity to do nutritional research with especially laying hens. So I'm just going to take you through what I have learned in my past 5 years, uh, five, 5.5, 6 years in North Carolina State as well as Mississippi State, and maybe give you some insight about the poultry and the challenges that we're facing. A brief background about what Salmonella is. Salmonella is a rod-shaped bacteria that is motile and gram-negative bacteria. So I presume all of you are having a background in veterinary sciences, and this is just a theoretical knowledge about how Salmonella, and it's from the family Enterobacteriaceae. And Salmonella is actually a genus. And this publication right over here, Garmont and Willie, is the major publication that classifies Salmonella. Salmonella is classified into two species, Salmonella bungori and enterica. And Salmonella bungori does not cause that much of cases. It's this species, Salmonella enterica, subspecies enterica, that causes a lot of problem to poultry as well as humans. With Salmonella, you do have diseases like the pullorum disease and other salmonellosis diseases that are not infected in humans but cause a serious problem in poultry. And this is also a part of Salmonella enterica, subspecies enterica, um, pullorum, or gallinatum. Now, the interesting thing I think for the next generation to do is this classification was done in 2007. And now we are thinking that this does not completely represent Salmonella as such. Because Salmonella, just think about it, Salmonella gallinatum and Salmonella enteritidis or Salmonella typhimurium, which causes diseases with human, is actually classified into the same species, same subspecies, and it's just a serovar that's different. So this does not really give us a good idea in how Salmonella has been classified till now. So I think the new generation would go into molecular classification, genetic classification of Salmonella rather than just being the serovars and serotypes. That will maybe give us a better understanding of how Salmonella can be divided and how we can develop approaches to compete or reduce certain groups of Salmonella. In total, there are more than 2,000 serovars of Salmonella, especially in the Salmonella enterica, subspecies enterica group. And that will be my main focus in my talk today. And this also applies to Salmonella enteritidis and Typhimurium infantis, these serovars. Now, some of the textbook also classify Salmonella as typhoidal and non-typhoidal, but that's not a good classification. You need either a genetic basis or something that can be linked through the mechanism. Um, and I think the genetic classification is what is needed at this point of time. So I'll run really fast because I have a lot of slides. So Salmonella, the poultry, especially laying hens usually. So Salmonella is a huge problem, especially with the laying industry. In the United States, what we do is we process the poultry meat. So while we process the poultry meat, it is dipped into the antibacterial solution that causes to reduce Salmonella or any other pathogen. But eggs, you cannot do anything because Salmonella can be inside the egg, and there's no way to decontaminate the egg. One of the practices that we follow in the United States is washing the eggs. Now, I know a lot of Asian as well as European countries do not wash the eggs. So there's a lot of controversy about should we wash the egg or not wash the egg as well. And I think that is open to more investigation, what would be the best route to control salmonella. But salmonella is usually consumed by the laying hens and it's carried on into the ceca. It's there in the ceca that salmonella can stay for a long time. And when favorable conditions arise, it can actually replace or displace the gut microbiota, also known as dysmicrobiosis, and then cause an infection. These are then converted into these vacuoles and then transported towards the body. What I have seen and a lot of researchers have seen is first the salmonella goes from the blood to the liver, spleen, and then there is a possibility of salmonella going into the reproductive tract. Although this is a very low possibility, there is a chance that your egg can be contaminated with salmonella internally. So salmonella usually has a mechanism of displacing the microbiota. That's how it gets an entry into the cells. It forms a salmonella-containing vacuole, and which is a point of replication for salmonella. And these macrophages engulf the salmonella and then take it to various organs as well as parts of the body. Now, this is strictly talking about the United States. Salmonella is a major cause of foodborne infection even in the United States. Every year, it is reported about 1.35 million cases of infection. That's about 10 lakh infection, 13 lakh of infection, 26,500 hospitalization, about 420 deaths. Now, this is really alarming for the United States as they are very cautious about the health system out over here. And the prevalence of salmonella, as I said, is very low in the eggs. The possibility of finding an egg positive with salmonella is about 0.05. But if you consider there are more than 9 billion eggs produced in the United States every year, this can possibly cause 500,000 potentially contaminated eggs. So that is why it is important. So yes, there are a lot of strategies to control salmonella. I think in Asia and in a lot of other countries, we still follow antibiotics. But in the United States and European Union, we are trying to go away from antibiotic because of the antibacterial resistance. So we're trying to find out innovative methods to control salmonella. One of the methods that have been used is vaccination. But the problem here is you cannot vaccine a bird late into the production phase. So because it is a live vaccine, so you can't vaccine a bird that in like, let's say 50 weeks or 60 weeks of age. And the vaccine that we've given at like 14 weeks of age really does not work throughout the lifespan. So that's why we are thinking of supplementing the vaccination with another strategy, most probably route through microbiota to help. And some of these key ingredients are prebiotic, probiotic, essential oil, symbiotic, precision biotics, phytobiotics, bacteriophage, fatty acids, and postbiotics. Now, the industry is going crazy with all these various things, but do they work? Or it's just an illusion of work. So that's what we are trying to investigate and see, and that's what my PhD was about. So what are prebiotics? Prebiotics are non-digestible carbohydrates usually. They are selectively utilized by the gut microbiota and they provide benefit to the host. A lot of people have a lot of definitions, but keep it simple. It's just a non-digestible ingredient by the bird, but digestible through the microbiota, digestible to the microbiota. And it is specially used to improve or to help the bird improve its health. You might have heard of mono-oligosaccharides. This is one of the most commonly used prebiotics in the poultry industry, fructo-oligosaccharides, and yeast cell wall products have gone crazy, especially in a lot of countries. So yeast it forms a byproduct of the brewery industry. So they have a lot of yeast that they want to find a use for, and they have shown some degree of use introducing salmonella, but still the evidence is not strong enough. So this is the exact mechanism how the prebiotic probiotics work. It's usually consumed by the bacteria, and usually production of butyrate is what really causes um, the salmonella to may not invade or maybe weaker in invasion of the intestinal tract. So the mechanism is through the production of butyrate, propionate, and acetate. Probiotics, most commonly a live microorganism, they restore gut health. And one of the main thing of giving a probiotic is it should be a live microorganism. Mostly these microorganisms have been Bacillus and Lactobacillus. There have been a lot of research um, with other bacteria, but these are the ones that have been consistently finding some help with regarding reduction of salmonella, and they help by improving the microflora, by adding the microflora. But is it sustainable? Is it always applicable? We don't know. So precision biotic is another area that I investigated upon. Precision biotics goes into the concept of microbiota one step further, where it says that it's not only the microbiota that's its influence, but the microbiome as such. And the influence on microbiome cannot be quantified by calculating few bacterial species. Certain bacterial species, lactobacillus, have certain mechanism that they help produce these short chain fatty acids. So these metabolic modulators, especially precision biotics, help to increase these production cycles of certain bacteria. So they are not bacteria focused, but they are more the metabolic pathway focused. And they focus on a pathway to to increase more short chain fatty acids like butyrate, propionate, and acetate, which is the exact mechanism how salmonella can be reduced. So one of the things that we are still trying to understand is are there alternatives to antibiotics that can be used to reduce or control salmonella and other diseases? And also they can be used to promote gut health or reduce some other pathogen. Let's say E. coli is another issue, especially with the laying hen industry. And can it help reduce salmonella as well as E. coli? So these are things we're still investigating upon, and a lot of people have positive response, but a lot have negative response. So I'm going to share what I found and what others say as well. So first of all, what happens is when you want to test the product, you want to do a small in vitro test just to see if it works on the salmonella itself or not. So first during my PhD, I conducted a series of in vitro tests to find out which prebiotic, which essential oil, and which probiotics can actually work on salmonella. So these in vitro processes, we need to stimulate the digestion process as closely as possible. And we can also account for microbial changes by including other microbiota in them. One of the advantages of using this is they can be poultry-specific pathogens. So we can use poultry-specific pathogens in the quantity we want just to see what the effects might be. And we can do a lot of things like co-culture technique in which prebiotic and probiotic can be added. There are, as I talked about, three prebiotics. There are more than three. There are like maybe 15 prebiotics. So you can really test and try which one works. And this is only possible if you have an in vitro setup. And I also worked on developing an in vitro digestive assay that can mimic the conditions of the digestive tract by mimicking the pH, temperature, and the enzymes, and how it can actually affect the salmonella and the prebiotic probiotic. So these were the three experiments that I did. First, we found the influence of different concentration of prebiotic and essential oil on the growth of Salmonella and Lactobacillus reuteri in nutrient broth. And the Lactobacillus, so I was talking about having a commensal microbiota, and Lactobacillus reuteri in our condition, we added to mimic the conditions of microbiota. Because for prebiotic, you need a probiotic for it to function. So we added a prebiotic. I can't tell you the product details because this is a proprietary product, but we added a prebiotic and essential oil, and we also added a lactobacillus for it to create a conditions like a microbiota. And then we also tried to simulate a digestive process to study the effects of probiotic, prebiotic. And one of the things that we found during my PhD is the role of calcium carbonate, which I will discuss more, and how it can affect the concentration of salmonella. So the objective was to identify the effective dose of the prebiotic and essential oil combination product to reduce salmonella in the presence of a commensal poultry bacteria like Lactobacillus reuteri. And this was done in an in vitro experiment. So in our experiment, we selected a nalidixic acid-resistant Salmonella enteritidis. Salmonella enteritidis because it is the one that is the most concerned in the United States and as well as in Europe, and definitely in parts of Asia and other rest of the world as well. And the commensal organism that we used was Lactobacillus reuteri, which was actually isolated from poultry in our department. And the prebiotic, I can't give you a lot of details, but this is what I can say about the prebiotic blend. It was a blend of chicory root. Now, chicory root is a source of oligosaccharides and yeast cell wall extracts and inulin. And the essential oil was cassia oil, oregano oil, and various mineral oils. So we had this complete experimental design was a completely randomized design with a 2x4 factorial arrangement of treatment, which had two levels of a commensal organism with lactobacillus and without lactobacillus, and 4 different levels of the prebiotic dose. So we had 0%, 0.5%, 10%, 0.1%, and 0.2%. So just going over the procedure real fast, we took XLT4. I think that's what's most commonly used in the United States, and I expect it might be the similar in Asia as well. But there are other plates that you can use as BGS and others as well. But I have found that the most consistent results are with XLT4. So if you're not using XLT4, I think that's a good way to start using and thinking about XLT4 as well. It is very selective for Salmonella. And we also added nalidixic acid. We then incubated it, then we took the typic soy broth with the Salmonella, and we also incubated the lactobacillus and MRS agar, and then we transferred it into MRS broth, and we took the lactobacillus from here. So we took an equal volume of lactobacillus, which we wanted to simulate the conditions of gut microbiota, and for pathogen we took Salmonella, and then we incubated for various time period and saw what the effects on of this combination was. So for this, for the sample solution, we had various concentrations of prebiotic added to this broth. So this was a nutrient broth, and this was done to simulate the digestive not the digestive enzymes, but the gut environment. Moving on, the data was log transformed and analyzed as a completely randomized design using PROC mix procedure, and PD mix 800 was used for various treatment comparison, and significance was set at p-value less than 0.05. All the plates were duplicated, all the tubes were duplicated, in fact, the tubes were triplicated, and the Fisher's LST was used to separate the mean. So moving into the results, I like to first set up my graph. So this x-axis shows the various time periods, and the y-axis shows the salmonella concentration in log CFU per ml. The blue bar over here shows 0%, which is our negative control, then 5%, then 10%, and 20%. What we observed was the 0% has a consistent increase in salmonella concentration, but the 5% and the 20% had the best effect at 8 hours, at 6 hours as well, and 4 hours as well. At 2 hours after incubation, we didn't see a much effect, maybe because it takes at least 2 hours for these prebiotics and probiotics to mix and actually start working competitively against Salmonella. This was the effect of the Salmonella concentration in treatment with lactobacillus and without lactobacillus. So as you can see, without lactobacillus, if there is no commensal organism, the salmonella concentration would be higher, even at 2 hours. And if you have a commensal organism, then the effects of prebiotic and probiotic is such that you could find a significant difference as early as 2 hours. So this really emphasizes the importance of mixing a prebiotic and a probiotic if you're doing an in vitro study, and also the understanding the role of gut microflora on reducing salmonella while using a lot of these feed additives. So this shows lactobacillus concentration. We observed that the lactobacillus concentration was slightly lower in the 0%, but all of them had similar concentration of lactobacillus, and we did not observe interaction or anything with the lactobacillus. This difference that started off at the start was maintained throughout the end. So we did not observe any difference with lactobacillus with the various prebiotics. So a lot of other experiments have also used the prebiotics and probiotics, and what we found was 0.5 and 0.20 was what was working best. Why one was not working? Maybe there is a logarithmic effect. Maybe there's um, we still don't know. And what we observed was 0.5 and 0.2 was the most effective, especially for our treatment. 0.1 maybe, but not as effectively. And this decreased the pathogen of gut bacteria and also increases lactobacillus species. We also observed that the higher doses of prebiotic can actually work against lactobacillus. So this was interesting to see. Now I'll just catch a little pace. So then we try to evaluate the effects of prebiotic on using an in vitro digestive model. So with this in vitro digestive model, we used a probiotic with bacillus species. And we had, so this was a completely randomized design with Salmonella enteritidis, prebiotic and essential oil, probiotic, and prebiotic, essential oil, and probiotic. So with this, we followed a method similarly showed by Latore et al., in which we took the feed sample, we added HCl to take the pH to 5.2. That's what the pH in the crop is, and then incubated for 30 minutes. So the feed actually stays in the crop for 30 minutes, and then we played it into MRS and XLT4. We then heated it. We then incubated it further, added pepsin, and incubated it further for 15 minutes. That's how long it stays in the stomach. We reduced down the pH to 3, and then we took that and we plated those samples again. Again, we took the same test tube, and then we added pancreatin as well as sodium bicarbonate now to increase the pH. Now this is to replicate the intestinal pH, and then we again took it and inoculated again. This was the procedure that we followed. Similar procedure as the last one was used for the statistical analysis. And what we found was the total salmonella count was reduced equally in prebiotic, probiotic, as well as the symbiotic. So as you can see, the negative control has an increasing concentration of salmonella as we move from crop to proventriculus to intestine. And all of the other treatments have a similar decrease in salmonella. And it's very interesting to note that the effects are actually consistent and not very, very drastic. So what the concentration of lactobacillus was, we found out, so lactobacillus needs a very acidic temperature, pH to thrive. And as the pH turned more basic, we saw a decrease in lactobacillus. And similar with bacillus, so the probiotic used was bacillus in this case. What we observed was the bacillus was highest when it was acidic. And as it became more alkaline, the concentration of bacillus decreased. So the lower pH might have had potentiated the lower pH might have made it more effective, the treatments to be more effective, as we could see the effects only after the proventriculus. stimulation of the preventiculus, and similar results have also been found with Bacillus species and Clostridium perfringens. So now we wanted to see, we were seeing some inconsistency in our results, so we wanted to see the effects of dietary calcium carbonate and prebiotic and some Salmonella concentration using that similar digestive assay. So we formulated two diets, a developer diet and a layer diet. And if you know about a developer diet, it has lower calcium as compared to a layer diet. A developer diet has about 1.2% of calcium, whereas a layer diet would have around 5% of calcium. So this was the diet we used in our experiment. And as you can see that the calcium level is statistically different in the developer and the layer diet, as well as the inclusion of limestone, which is the source of calcium in these diets. So what we observed was interesting that in the probiotic group, the developer diet had lower Salmonella enteritidis concentration as compared to the layer diet. So that's what this shows is the layer diet is not effective enough to reduce Salmonella. Why can that be? One of the things that we thought is the level of the effect of calcium carbonate. You know, whenever you have calcium carbonate, it acts like a buffer. And when the gastric pH tries to decrease below 3, it acts as a buffer. This might be allowing the Salmonella to survive. This opens a new idea that a lot of these Salmonella infections can actually be seen at 14 to 16 weeks of age in pullets. That may be because now they're changing diets from low calcium to high calcium diet. So this might be an effect of calcium carbonate that is causing a lot of these Salmonella outbreaks in pullets, you know. Now we wanted to establish a challenge model in which we wanted to investigate the impact of Salmonella inoculation on fecal shedding, tissue colonization, and gut microbiota in vaccinated and unvaccinated laying hens. Vaccination strategies have been very consistent and have been used throughout. But one of the things that we have less understanding is about the interaction of microbiota and vaccines, as well as the effect of vaccination history on supplementation of prebiotic and probiotic. So for this, we collected the fecal sample, tissue sample, as well as the fecal microbiota. So we did two experiments in this. The first experiment, birds were vaccinated with Polvac ST, which is the live vaccine used for Salmonella in the United States. And we used Highland W36. They were 30 weeks of age, which were divided into 3 treatments on the non-challenge, challenge with 10 raised to the power 7 and 10 raised to the power 8. And in the second experiment, we did the not vaccinated one. And these were 35 weeks of age and similar, but we increased the dose a little bit because of our results from our previous experiment. So I'm going to show more. So we had these challenge cages in which birds could be kept individually and then challenged. And these were a set of cages which we used for our experiment. We had 2 birds per cage, and this served as an experimental unit. These were blocked as per the levels. Also, before the experiment, we screened all the birds for Salmonella using a rapid Salmonella detection kit. And all the birds using all my experiments had been negative for Salmonella before the start of experiments. We used the nalidixic acid resistant Salmonella, which was revived from a frozen sample in a triplet broth and was plated into an XLT4 plate with 200 ppm of nalidixic acid. Then it was again transferred into the triplet soy broth, and this was done to calculate and it was actually done for 12 hours so that we could know the concentration, and we verified the concentration using the absorbance, and that's how we got to know what was the actual concentration of Salmonella in the challenge we used. We used a 7-day adaptation period, and then we challenged the bird 2 times, one day before the start of the study, or let's say day 0, and one day at day 1. What we observed was repeated challenges needed for Salmonella to stay, because these Salmonella are so they do not cause an illness in chickens. So that's
Sorry
why.
for interrupting you. Actually, we have a
Mhm.
basic plan right now, and we will
Okay.
rejoin the meeting right at 8:40. So everyone can join the meeting again by the same link right at
Mhm.
8:40. Sorry for the inconvenience.
Okay, okay, that's all right. That's all right. Yeah, no problem. So, do you want me to go ahead till 11:40?
Yes, 8:40. Yes, 11:40 at USA. Right.
Okay, okay.
Okay. Thank you.
So liver, spleen, ovaries, and ceca were collected, and then we used the modified NPIP method, in which we took the fecal sample, weighed the fecal sample, added an equal dilution of buffer peptone water, which was 1:10. Then we divided into RV broth and TT broth. These are two broths used for salmonella culture in the United States. And then incubated it for a certain time, and then took the serial dilution, and then plated in 0.1 into nalidixic acid to resistant plate. So we did the similar thing for organs, but in the organs, we only did the treaty broth because so for the fecal sample, the salmonella goes through a lot of challenges, but for the tissue sample, the salmonella is not that stressed. So for that purpose, we only use the TT broth enrichment method. So I will let you guys leave, and I can continue to discuss more about this at a later time. All right, thank you.
Okay. Thank you. We will just came back
Mhm.
at 8:40.
Okay.